particles. These are really vibrations in quantum fields. We only associate mass with them when they become real particles later on. So when we're putting these virtual particles inside our Feynman diagrams, they don't need to have the masses that the particles usually have. However, remember, the whole point of the Feynman diagram is to calculate a number, the rate at which this interaction happens. It turns out that if the particles inside the diagram have masses that are close to the masses that the real particles would have, the contribution from that diagram will be larger. This sounds like it's not going to be very important to your life because you're not going to calculate any of these diagrams, but later when we go looking for the Higgs, this will become a very important fact. Another important feature of virtual particles is that it lets us have loops inside Feynman diagrams. Remember, we have the simple thing where, let's say, an electron and a positron scatter by making a photon and then they go their separate ways. But they could also scatter by emitting two photons. And what's happening there is we're actually summing over all of the possibilities. So summing over all the possibilities doesn't just mean draw all the diagrams. It means that for every diagram where there's a loop, you sum over every possible way that energy and momentum can flow through the lines in the loop. In mathematics terms, that means you're integrating, you're doing calculus and integrating over all the different possible ways that momentum can move through the diagram.